Aldehydes can also be identified using the Fehling or the Benedict test. In both tests, the aldehyde group is oxidized to a carboxylic acid, and it reduces a metal compound. So the Fehling test uses tartaric acid to complex copper 2+, and the Benedict test uses citric acid to complex copper 2+. So all three tests are used to distinguish aldehydes from ketones. These tests will give a positive result for aldehydes and a negative result for ketones. Notice these are ketones over here, and you get no test result whatsoever. So if we use propanone or acetone in the Tollens test, nothing happens. If we would have used an aldehyde, it would have deposited silver. Here we use pentanal in the Fehling test, and we reduce copper 2+ to copper 1+. And that is proof that the reaction occurred. Reduction. Aldehydes and ketones are easily reduced to alcohols. Your common reducing agents are lithium aluminum hydride, sodium borohydride, and hydrogen gas on nickel. In general, aldehydes are extremely easy to reduce, and sodium borohydride or hydrogen gas will easily reduce them. Then you end up with a primary alcohol. These molecules will also reduce a ketone to a secondary alcohol. Lithium aluminum hydride is a much more active reducing agent, so that will reduce the carboxylic acid all the way down to an alcohol too. And so that's actually a much more powerful compound than sodium borohydride. So even if you take organic chemistry as an undergraduate, you're probably not going to use lithium aluminum hydride, and you'll probably use sodium borohydride because it's a more gentle reactant. Reduction and oxidation in biochemistry. Pyruvate acid is reduced to lactic acid in muscle cells. So we have pyruvate, which is the end product of glycolysis. You start with glucose, and then there's a 10-step process which yields 2 molecules of pyruvate. However, if there's not enough oxygen in the human body to act as the final electron acceptor, to try and recycle the NAD+, and NADH will deliver its electrons to pyruvate, reducing it to lactic acid. And this frees up an NADH into an NAD+, which can then be used to do more glycolysis. So this is fermentation. An organic molecule is taking the place of oxygen and is your final electron acceptor. So instead of oxygen getting the electrons, whoops, that's a bad drawing, because it strikes that ketone group. So those electrons attack there, kicking these electrons up, forming this alcohol, lactic acid. And so when you're working out super hard, you make lactic acid because you're actually burning fuel so quickly you can't get oxygen to the fuel. And that's when someone says they're in shape or they're out of shape, that's what they mean. The more you work out, the more vessels your body builds to feed oxygen to your muscles and to the areas that are burning fuel. The more oxygen you get there, the cleaner the fuel burns. If there's not enough oxygen, you don't break your glucose all the way down to carbon dioxide anymore. You only break it down to lactic acid. And then when you're done working out, this lactic acid will go back to your liver and get reoxidized to pyruvate again in the Cori cycle. And then, while you're resting, you can break it down all the way to carbon dioxide. So write the structures of the products of the following reaction. Propanone and lithium aluminum hydride gets reduced down to the alcohol. So propanol, 2-propanol. Pentanal and lithium aluminum hydride, we get pentanol. And this drawing only shows 4 carbons. It actually should be one longer to have 1, 2, 3, 1, 2, 3, 4. Actually, it should be 2 more. Because pentanol has 5 carbons. So 1, 2, 3, 4, 5. And so that, we just erase that. And that would be our compound. So we'd have 1 carbon, 2, 3, 4, 5. And then that aldehyde group would be reduced all the way down to a hydroxyl group. Whoops. Let's get back in there. All right. Addition reactions. The addition reactions of aldehydes and ketones. We can form hemiacetals, hemiketals, acetals, and ketols. We also make cyanohydrins, aldols, and beta-hydroxyketones. Let's look at all of these. So a hemiacetal. This, we start with our aldehyde. And if either an alcohol or water attacks, we form a compound like this. There's one OR and one OH. If it's a ketone, you get a hemiketal. If it's an aldehyde, we get a hemiacetal. And again, coming off of this carbon, there's one OH and one OR. A full acetal has 2 OR groups coming off, and a ketal has 2 OR groups coming off. So here, methanol can attack, kicking these electrons up, forming the hemiacetal. And then the hemiacetal, this water, can again gain the proton. That's why you have the acid here, because you need that catalytic acid. And then this methanol can attack this carbon, kicking off the water, forming the full acetal with 2 methoxy groups coming off of it. This happens a lot with sugars, and so when you see the glucose structure drawn, it's typically drawn in this cyclic structure, and that's exactly what's happening. It's actually forming the hemiacetal. So here we see, this is 1, 2, 3, 4 carbons, butanal. We react it with 1 equivalent of ethanol to get a hemiacetal, 1 ethoxy, 1 butanol. And then we could react it with another equivalent, and we get 1,1-diethoxybutane. And now we have the full acetal. Hemi means half, so hemiacetal. We have 1 of the ethoxy groups, but now we still have this OH group, and so we can still add 1 more ethoxy group there. Addition of hydrogen cyanide gives you the cyanohydrins. Cyanide will attack the Cn- portion. We'll attack that positively charged carbonyl. Remember, this carbon is positively charged because the oxygen is pulling up on the electrons. So negative things can attack, kicking those electrons up, forming the cyanohydrin. If we attack a ketone, the cyanide group attacks here, kicking these electrons up, forming this cyanohydrin. Hydrolysis yields an alpha-hydroxy carboxylic acid. So if we have a cyanohydrin, and we hydrolysize it with acid, so we react it with acid and water to break it apart, we can finally oxidize this cyano group into a carboxylic acid group. And so the C triple bond nitrogen can become a carboxylic acid group, giving us an alpha hydroxy acid. We use the word alpha. When you have a carboxylic acid, or even with a ketone, the carbon next to the carbon with the double bond is your alpha carbon. So that's an alpha carbon. That's a bad alpha. Next carbon is your beta carbon, then your gamma carbon, then your delta carbon, And then 5 carbons out is your epsilon carbon. So it doesn't count the carbonyl carbon. The next one is the alpha, then the beta, then the gamma, then the delta, then the epsilon. And aldehydes have a hydrogen on one side, so we can only do this on one side of them. And same with carboxylic acids have an OH group terminally, so you only have one chain coming off. But for a ketone, you can count in both directions from the carbonyl group. So write the structures of the following products. We have cyclohexanone reacted with hydrogen cyanide. And the cyanide attacks the ketone group, kicking up those electrons, forming the alcohol. Aldol condensations. This is a self-addition. Aldehydes are ketones that contain alpha hydrogens, may add themselves to another alpha hydrogen containing aldehyde or ketone. These alpha hydrogens are more acidic than normal, and so they can be removed, and there's a lot more chemistry there because of that. So alpha protons are much more acidic than you would normally think. And because of that, they can be removed, and when you do that, you get the enol form. So instead of your carbonyl group, if you remove this proton, so we take that proton, these electrons come in here, pushing these electrons up, we get in what we call the enol form. And those are tautomers, a different form it can take. And there you go. And then these electrons can come back down, forming your carbonyl group again. And these electrons can attack another aldehyde, which is why they condense. So that's why this one attacks this one, condensing them. And here we see more of the mechanism. Again, alpha protons are much more acidic than you would think. They're easier to remove, putting a negative charge in this carbon, and that negative charge can then attack the carbonyl, forming our condensation product. So ketones with alpha hydrogen atoms also undergo aldol reactions. Same exact thing. Again, alpha protons are much more acidic than normal protons attached to carbon, so they can be removed, putting the negative charge in this carbon, and that negative charge then attacks this carbon, pushing the electrons up, forming the alcohol group. So pentanal. And there's a typo here. This hydrogen should be on this carbon. This is your alpha carbon, this is the more acidic one. So ignore what the publishers put there. The beta carbon is not going to be extra acidic. If there's a double bond here, then the system is conjugated and we'll look further back. But without another double bond over here, really we're looking at the alpha carbon. They should be taking a carbon off of here, and the negative charge should be on this carbon. This is the one that should be binding. All right, the conversion of 2-pentanone to 2-pentanol is an example of reduction. You're putting hydrogens across that C double bond O bond. Aldol condensations in biochemistry. The strength of collagen depends on aldol condensation reactions. The cross-linking bonds form a strong network. Collagen is a triple helix, and typically it's a repeating unit of amino acids. There's a lot of proline in there, and every third amino acid is typically glycine because all 3 strands cross in a triple helix, and glycine has an H as its R group in the amino acid. And so glycine is really the only amino acid small enough to fit 3 together like that. And this forms a structural component. It's your major structural connective tissue. Stronger than steel for its size in the body, it is one of the most important structural tissues. Formaldehyde. Here the IUPAC name is methanal, and we can synthesize it from methanol and oxygen, just oxidizing methanol over vanadium oxide. It's marketed as a 37% aqueous solution of formalin. And we make 1.33 times 10 to the 9th kilograms. It's 1.33 billion kilograms of this are made in the U.S. every year. Acetaldehyde, the IUPAC name is ethanal. It has some narcotic action, which is why a person can overdose on alcohol, and it can cause respiratory paralysis in large doses. And so when somebody drinks alcohol, it gets oxidized first to ethanal, and this has a lot of toxic symptoms on the body, which is why too much ethanol can kill a person. Its principal use is an intermediate in making other chemicals, such as acetic acid or 1-butanol. Acetone, IUPAC name, propanone, manufactured by the oxidation of 2-propanol. Used as an organic solvent in the manufacture of drugs, chemicals, and explosives. It's used a lot in the plastic industry, and it's a good remover of paints, varnishes, and fingernail polish. Methyl ethyl ketone, MEK, you can see that at Home Depot. It's used as a solvent, and it's especially useful for lacquers. And it's manufactured by oxidizing 2-butanol into 2-butanone, or methyl ethyl ketone. Condensation polymers. These are produced when a small molecule, such as water, is eliminated during polymerization. And there's some important classes: polyesters, polyamides, and polyurethanes. And phenolics, polymers made from phenol. Bakelite is an example of a phenolics. It's a phenol formaldehyde condensation polymer. It was first marketed a century ago, and it was used in electrical equipment because of its insulating and fire-resistant properties. And that is the end of this chapter.